Welcome. Over last few lectures, we have looked into the algorithms for different solution methods, both direct and iterative way for matrix equations. However, these algorithms are designed to solve large matrices which we really cannot handle using simple paper and pencil, and as we have mentioned this several times, a good solution technique should be also designed keeping into mind that it has to be translated into a computer program. So, in this particular session and also in the subsequent class, we will start looking into how we can make computer programs from these solution algorithms. So, mainly look into C programs, but any programming language as well as the programming platforms like MATLAB can be used for writing these programs, and you will see plethora of already written programs in Jacobi algorithm for Gauss-Seidel or for the algorithms we will discuss in future like biconjugate stabilized algorithm or generalized minimum residual algorithms. Plethora of examples are there of these algorithms translated into computer programs in different languages: C, C++, Fortran, Fortran 90, Python as well as MATLAB, R, and these are well available in internet resources. So, sometimes we pick these algorithms from open source codes available in as internet resources and plug it into the particular application we are trying to develop. And sometimes also they are in form of some software or some executable built using the source code is not available to us, only the executable, which uses essentially these algorithms for matrix solutions, and we plug call those softwares, we plug this executable with our program and run it. Nevertheless, it will be important to look into inside the program and what is inside the code. So, we will primarily look into few examples using C, and also we will look into few Fortran implementations and see how different variants of similar solution technology, like for basic iterative method, how different variants Gauss-Seidel, Jacobi, SOR can be written as computer programs, and later we will see how the generalized projection processes like steepest descent, minimum residual method, etc. also come, and when we will discuss about conjugate gradient, biconjugate stabilized, we will also discuss about those algorithms. Right now, based on the understandings we have built and the algorithms we have yet covered, we will concentrate on a few of the basic iterative algorithms, and we will start with Jacobi, Gauss-Seidel and SOR in this particular lecture. So, this is on computer programming for basic iterative methods. So, if we look into the Jacobi iterations algorithm, we are solving a matrix equation X is equal to B, and as we know A is diagonally dominant or irreducibly diagonally dominant for implementation of this particular algorithm. And in a Jacobi method, the ith row of the matrix in general, the ith row of the matrix is given as a sum of Aij xi is equal to Bi. Now, let us assume a Gauss solution x is equal to x 0 for different values of the different elements of the vector x. We start with a Gauss solution, and for the levels of k, which are the iteration levels, k is equal to 0, 1, 2, we update x as xi k plus 1 is equal to Bi minus Aij x j k, where j is not is equal to I. So, for all off diagonal Aij, we multiply it with the corresponding x and divide it by Aii, and we iterate it. So, we get a k, so we start with x 0, we got x 1 using x 0 here, and then with x 1 we get using x 1 here we will get x 2, using x 2 here we will get x 3. So, we are updating all the elements of the vector x at different level, and we will do this till we get convergence, that is xi k minus xi k plus 1, its absolute maximum of the absolute value is less than epsilon. And we have seen that once this value converges to a very small number, the equation Aij xj is equal to Bi or the residual of the equation, that is Bij minus sum of Aij xi for each row of I also converges to 0. So, convergence of the x vector also imply that the residual will converge to 0 or the equation will be approximately satisfied to a high accuracy based on the parameter epsilon, and this epsilon usually depends on machine accuracy. It is something, it is a small value, it is say 10 to the power minus 8, 10 to the power minus 12, 10 to the power minus 16, etc. It is based on what type. If you are using single precision variables, we usually stick to 10 to the power minus 8, but there are certain cases using double precision and double precision computer and high accuracy algorithms, we can go for higher level of the value of 10 to the power minus 16. So, epsilon is a small number, the differences between the present value and the updated value of the x vector must be small. That is the idea which we will carry forward. The operational steps, main operational steps we will look into this particular case. For every at any iteration level, for every element of x or every row of the equations, we have to find out xi k plus 1 is equal to bi minus sum aij xj, j is not is equal to I divided by aii. That means, this sum has to done for all the elements in a row or for all the members of the vector x. If the x, if I have a 2000 by 2000 matrix, x has 2000 elements. So, this summation has to be done 1999 times except the diagonal term, and this now this operation has also been repeated for all the rows. So, sum of for large number of j is not is equal to I for each of the I rows. So, we have to do it for 2000 I rows, and in each row we have to do it for 1999 times. So, it is a large number of operations if we think of doing it manually. And also the update of k plus 1 is and xk, this k plus with different values of k, I will find out x at different iteration level. This update has to be found out till this value is less than epsilon, which is also a large number of iterations has to be done, and we will see some example that iteration numbers can go up to few hundreds, few thousand, 10,000s also, depending on the matrix size and the nature of the matrix. So, for large values of k, this has to be operated. So, large number of steps are to be followed for large matrices, both in terms of the multiplication and finding out xi k plus 1, as well as the same operation, this operation has to be looped over a number of iterations till we get a high value of k, so that the solution converges. So, sum of computer programming for Jacobi method will essentially have few important steps. Sum of all the terms in each row, that is looping the sum over all rows to update each element of vector x. So, we have to find out for all j's in one particular row, and then we have to loop it over all the rows to find out all each elements of vector x, and then looping this update for large k times till convergence. So, once we do this, this is only one step and it will not converge to the right result. So, we have to loop this for several times till we get a converged solution. Also, you need to store old values of xk. Once it will be used to compute the updated xk or xk plus 1, and as well as it has to be compared with the updated x. So, what I will say that xk, x at kth level has to be stored to calculate x at k plus 1, as well as, but once we calculate this, we cannot discard this variable, because this will be further needed to compare with xk plus 1 in the way we have to see what is the max of I xi k minus xi k plus 1. Is this less than epsilon or not? So, you have to also compare the variables at different levels. So, these three are the main steps when you will think of a computer program, and a computer program essentially does few arithmetic calculations like addition, multiplication, division, etc. And also there are logical loop, logical gates, like if the value is less than epsilon, then we will say that the solution has converged and will not carry forward the calculations. If it is greater than epsilon, then we have to again go back to the previous type set of operations, that means calculating of x k plus 1 using x k. So, we have to loop over the rows to calculate x k plus x I k plus 1 for different value of I, and again we have to put a loop of calculation of x k plus 1 x I k plus 1 for a large number of values of k. Once we get it, we will start with k is equal to 0, we will calculate x at x 1, we will do, then we have k is equal to 1 and we will calculate x 2 and so on. So, we have to loop it over the values of k also. So, there are two loops, similar operations has to be done again and again in these two loops, and there is an important logical step, that whether the value is less than epsilon or not. So, we will as an example we will look into a 2D Laplacian problem using Jacobi method. We are solving del 2t, essentially del 2t del x square plus del 2t del y square is equal to 0, and the boundary conditions are given, t is equal to 1, t is equal to 1, t is equal to 0, t is equal to 0. As a matter of fact, you can give any boundary condition of t here. When you convert it using finite difference, when you convert it to a matrix to a difference equation, t I minus 1 j minus 2 t I j plus t I plus 1 j by x square plus t I j minus 1 minus 2 t I j plus t I j plus 1 by dy square is equal to 0. And if dx is equal to dy, we can write t I minus 1 j plus t I j minus 1 minus 4 t I j plus t I j plus 1 plus t I plus 1 j is equal to 0. Now, what we have to do? We have to express this in the matrix form, and we have discussed this earlier. We renumbered the points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, so on. So, this particular point, which is 19, 20, 21, 22, 23, and this will be 32. So, this particular point will give us a, this is 24 matrix equation, where there will be T 24, T 32, T 14, T 24, T 22, and we will get a matrix equation A t is equal to 0 for the 23rd row. All the terms will be 0 except 23, 22, 23, 23, 14, 22, 24, 22, 32, 22. We have discussed this earlier, that we can express it now as a matrix equation, and we will try to solve this matrix equation using a Jacobi method first, and then we will see how this can be modified to Gauss-Seidel or SOR. So, this is how the equation for each row, and when we will write it in a matrix, we will get a pentadiagonal matrix, few minus 1, 1, 4, and like multiplying minus 1 with here to get the positive diagonal term. It could have been done similar with the negative diagonal also, because the absolute value of the diagonal is important, not the value of the diagonal. The sign is not important to look into diagonally dominant. So, this is a diagonally dominant system, as when we will apply boundary condition, the boundary terms we have 4 minus 1 1. So, 4 is greater than sum of them. So, this is a diagonally dominant system. So, we get a row like this, and how can we solve this equation, and then we will have a matrix like this, and we will put the boundary conditions to make the matrix non-singular and diagonally dominant, and try to solve it using a Jacobi method. So, what we will have to do in Jacobi method? We have to find start with a guess value of x, find the updated value of x for each node, for each of the points we have to find out the updated value of x. Then we will check whether the updated value and the previous value are very close to each other. If not, then we have to take the updated value as the guess value, and then we have to find out the next updated value. So, we have we can look into a Jacobi code, maybe I should come out of this and open this in a notepad plus plus, which is more well visible. So, I should go to so this is the Jacobi code 2D Jacobi dot C. I just have to improve the font size. I hope that this is better visible now. So, this is the 2D Jacobi code, and it starts with all the header files you need for calculation for a C program, especially the math and time are important, because some mathematical functions will be included, and we are also trying to measure the performance of the code, in a sense how much time it has taken. So, you have to enter a size of the mesh. We took a 2D mesh with same number of points in x and y direction. So, what will be the total number of points, and you define the file mesh based on that. And now you this mesh is basically, mesh will take basically the x and y coordinate, x, I and j index of one particular point, and then with mesh I will not locate this point into one particular, like from 2, 3, this point, what is its absolute location in this mesh. So, based on this we will form the A matrix A, and this A matrix will have 1 in the off diagonals and -4 in the diagonal term, and all other terms in the A matrix will be 0. So, we have initialized the A matrix as 0, and these terms are 1 and -4, and we also put the boundary conditions. We read the value of temperature, which are the boundary conditions at for the side walls and the top and bottom wall, and substitute this into the equation. So, up to here we have got the A and B, A matrix and B vector. Then the next step is that you use initial value of x, the initial case all the x's are made to be 0. It could have been made anything in a Jacobi program, but here we try to make all the x's to be 0. So, enter the desired accuracy. Will ask for what will be the accuracy or what is the value of epsilon, specify epsilon, what should be the value of epsilon, and it is read as epsilon. So, the user will have an input that whether he will try to get a convergence up to 10 to the power -4, x k plus 1 minus x k is of the order of 10 to the power -4 or 10 to the power -8 or 10 to the power -12. We will specify the value of epsilon like that, and an error is calculated as twice of the epsilon. A clock time is started to take care of how much time it is taking, etc. So, and the loops are done where error is greater than epsilon. Initially we took some error twice epsilon, but later we will find out the error, and in calculation error, that means the difference between two the values of x at two different iteration level, whether this is greater than epsilon or not. If this is not greater than epsilon, the loop will not be done, and iteration count, number of iteration is less than 1500 or not. If we go for more than 1500 iterations, we will say that this is not converging, and we will come out of it in this particular code. So, error is xk minus xk plus 1, and the maximum value of, because xk is also a vector, xk plus 1 is also a vector, their difference is a vector, maximum value of that vector is L infinity norm. We will take this as the error, and this should be less than epsilon for the convergence. The next step we do for k loops, we start with k is equal to 0, and go for k less than n and start adding k, and later you can see the variable count is advanced in each iteration. That means, if k is equal to 0, count becomes 1, k is equal to 1, count becomes 2, etc. Count is the counter of the number of iteration. It increases exactly same way as k increases also. Now, what we have to do in the iterations? We have to find out this summation bi xi k plus 1 will be bi minus xi j aij xj for j is not is equal to I. So, we will do these summations aij xj up to the diagonal term. Start with ai1 x1 and do up to aii x before aii x1 ai minus 1 xi minus 1. We will do this sum, and then also we will start the sum with ai I plus 1 xi plus 1 and go up to ain xn. So, this sum is broken into two parts, one is up before the diagonal, another is the terms after the diagonal. We can see the program that is sum is equal to is the sum aij xj into x0, and this is done for j is less than I, and then this is done for j is equal to I plus 1 to j is less than n. So, except I is equal to j, the terms are summed, and this sum is subtracted from bi and then is divided by aii, which gives me x1. x1 is the updated value of x. x0 was the guess value, x1 is the updated value. So, we will find out what is the absolute value between x1 and x0 for 0th vector, and then we will find it out for all other vectors, and if the for the 0th element we will find it first for 0th element, and then we will check for which it is maximum. If it is maximum for first element, then error is replaced by x1 minus x101. If it is more in second element, error will be replaced. So, that is why we will find out the maximum value of the error, which is maximum value of xk plus 1 minus xk or x1 minus x0 for but look, this k is not the iteration level k, this k is the element number in the vector x. And here our iteration loop ends, so that the iteration counter will go and check whether count has been added by plus 1 1, where count is less than 1500, that means 1500 iterations are done or not, and error is greater than epsilon. And once it is done, it will come out, and once the error is less than epsilon, then this will not be satisfied. That means the program has converged. The x1 and x0 is minimally far away from each other, the difference is less than a number which we have thought already. So, we will write down that this is the count and this is the error, and we will write down the results. So, this is what we get in the Jacobi iteration method. Now, we will look into few other methods. So, this is what we got in Jacobi iteration. Now, we look into the Gauss-Seidel method. A is a diagonally dominant matrix, same thing, ith row is aij, aij xi is equal to b, and we will start with xi is equal to x0, but update is not xi k plus 1 is bi minus j is not equal to I aij xk ii. Rather, the update will be xi k plus 1 is bi minus j is less than I aij xj k plus 1, because these x's are already available, minus aij xj k. So, this is done based on the values already known to us, and then we will do the same loop it till we get convergence, that means maximum value of this is less than epsilon. In the next session, we will look into Gauss-Seidel and Jacobi and successive over relaxation method, which is these codes can be very easily obtained by slight variation of Jacobi method, and we will also look into a different class of method which are the generalized which are the general projection methods like steepest descent, minimum residual, etc. Thank you.